today I have the pleasure of being joined by Assistant Professor Sownak Bose. How are you doing today, Sownak?
Good morning, thanks. I'm doing very well, and I'm very happy to be in this very fancy studio.
Yeah, it feels fancy to me too. So you do research using supercomputers to study the formation of galaxies, is that right?
Yeah, exactly. So it's galaxies, and I suppose more broadly, just understanding how the universe that we see around us has come to form over billions of years, and that's a very complex problem. So we put many very powerful computers to our use for that. So that's roughly what my research is about.
So is there like any reason in particular you're drawn to this kind of research? Like why galaxy formation, you know?
That's a good question. I mean, I think, when you're young and you kind of think about what are things in sort of the world or in your existence, I guess, that excite you, then these sort of questions about what our origins are and where we come from and, what the basis for life and all these kinds of things tend to be sort of the questions that, anyone's kind of interested in. And it turns out that astronomy and cosmology, which is broadly the subject in which all of this falls under, is quite a broad topic which actually taps into a lot of these questions. But beyond just delving into these questions in a philosophical point of view, you can actually write down scientific theories and mathematical equations that help express these questions and their solutions in some coherent ways. So I think it's a very exciting subject in that sense, because you can make these theoretical calculations, and most importantly, you can actually then take telescopes and then observe the real universe and see whether these are correct and make predictions and improve your theories that way. So it's a really exciting subject because you really tap into the most fundamental questions underlying human existence in some level in a way that can actually be tested. So I can't think of a subject that's more exciting than that.
Yeah, I think especially when you can have sort of equations to really pin stuff down, it makes it feel a lot more tangible. Maybe that's just a math student in me talking.
Yeah, no, but I mean, I think that's right, because, to sort of understand anything, we basically need to come up with the words or the language to express ourselves or to be able to query the laws of nature, and mathematics turns out to be one way to do that. And we, over centuries, have developed some of our methods to describe, say, the laws of gravity and the laws of thermodynamics and so on, which are, we think, these fundamental laws that dictate how stuff in our universe forms, and we can basically use that to our advantage. So really, it is a very powerful way to sort of try and tackle these questions.
Whenever we have to rely on sort of more qualitative ways of describing things, I kind of have a feel it feels like a bit of a cop-out,
Yeah, and I think at some level there is a place for both of these things, because I mean, if you really want to talk about the origins of the universe right from the very first moment that it came into existence, and one way to describe this is this idea of the so-called Big Bang model. I think even at that regime, our mathematics, despite how sophisticated it is, it reaches a sort of finite level of usability and predictability, and there is some physics around the very origins of our cosmos that we don't really have the full grasp of. And I think there are many qualitative arguments that are made that become useful, and hopefully one day we'll be able to quantify these. So I think there's always room to sort of have some kind of complementary approach between the sort of rigorous hardcore stuff maybe that we're able to write down in equations, and the stuff that we kind of just think about and hypothesize and are eventually then able to test.
Yeah, I think it's important as well, because the sort of quantitative stuff doesn't really appeal to quite a lot of people. It seems like very kind of complicated and a mess. People don't really want to get into that. But if you can describe more qualitatively, we think that there was a huge period of inflation at the start in the early period of the universe, that's a lot more, I guess, accessible to a wider range of people.
Absolutely, and I think that's where astronomy is a really unique subject, because I mean, just the images that come from space and from cosmos and stuff, they're so inspiring, right? And it's sort of so dramatic to see these objects which we think were formed, a few 100 million years after the birth of the cosmos, and the images that we are seeing taken by, these new space telescopes like James Webb and the Hubble Space Telescope and so on, are essentially snapshots of galaxies as they looked like tens of billions of years ago. And they have these sort of glorious, beautiful structures that, just beyond the aesthetic quality, actually tells you a lot about the physical processes that led to the galaxy looking the way it does. I think having this sort of visual comparison as well is a really nice way to sort of, I think, be inspired and in awe of what the universe gives us. So, I think even for me, who deals with the numerics and the computing and stuff like that, having that sort of visual element of being able to see the science and the physics before your eyes is the most amazing thing.
I think it's quite crazy to think how, like, kids growing up these days, like, they see pictures of galaxies and planets and all that from Hubble and all these other telescopes, and that kind of informs you of, like, oh, this is what I guess the universe looks like. But going back hundreds, like thousands of years ago, people just didn't have that. Right? No,
exactly. I mean, even our sort of knowledge of there being other galaxies and places like, say, the Milky Way, where our planet is found. I mean, that knowledge doesn't go all that far back. It's really just a 20th century, early 20th century thing, and ability to slowly be able to measure distances to different celestial objects that gave rise to the understanding there are these other so-called extragalactic nebulae, as people used to call them back in the day, because nebulae were basically these surfaces of stars that had been blown out and created these very spectacular looking images, like the famous pillars of creation image of that Hubble has taken and James Webb has taken, and so on. So people knew of those, but didn't know that there are other island universes, which was the term that was used to describe these extragalactic nebulae, even existed beyond our own. And that's, going back about 100, 200 years, so it's not all that far back.
Yeah, I think it really sort of changes the way we view, I guess, our place in the universe. Because, like, before that, it seems like the natural assumption people make is that, I guess, Earth and the Milky Way and all that is really special. And, like, not that it isn't. Mm-hmm. But, I mean, there's, I guess, when you know that there are countless more galaxies and planets, then I guess in a way it becomes maybe less special.
Possibly, yeah. I mean, I think there is this, there's a danger of people falling into this sort of peril of despair at some level when you sort of think about the magnitude of what exists in the cosmos beyond just ourselves, because, there's, we think many planetary systems like our solar system in any given galaxy. There's many stars in a galaxy, and there are many galaxies in the universe. If you just keep adding those up, then we become just one tiny speck in a very, very vast number of possible places where life or things like life could exist. But I think you have to kind of detach yourself from that a little bit. Otherwise, you just become like, well, what's the point of any of this really? Like, if we are just so insignificant, because after all, in our day-to-day lives, it is really essentially everything that exists within the little, oblate spheroid of our Earth that ultimately dictates what our entire existence is about at some level. So I think, it isn't incorrect to maybe sometimes feel overawed by it, but ultimately, what matters most to us is probably just the stuff that is happening in our day-to-day lives in and around ourselves.
Yeah, it's just like there's loads of different kind of like magnitude scales on which you can look at things, right? Like, I remember reading something that was saying about how if you look at individual cells really zoomed in, it'll tell you like nothing about like the overall kind of biological system they might be part of. Mm-hmm. But in that cell, it's like a whole kind of self-contained world almost. Right. And it's not until you zoom out that you see more.
How everything sort of fits in, like the little cogs of a wheel, making the machine run. Yeah, absolutely.
Okay, so I guess, can you tell me a bit more about your research now? Like, when I hear like someone's an astronomer, the first thing I think of is, looking into telescopes all day and all that. Is that accurate?
Right. It is possibly accurate for a certain branch of astronomy. So I think even the sort of romantic view that people have of, having these really powerful telescopes that you peer through in the middle of, the deep of night in some desert in Chile or something like that, then, I think that particular manifestation of astronomy is probably less accurate these days, because the biggest telescopes and the most powerful telescopes that are used by astronomers are mostly kind of robotically controlled and can be remotely controlled. And of course, you can peer through them and see stuff, but it's very rarely just one person and their telescope standing in the middle of the desert looking through to see what comes around. So I actually don't do much of that myself. So my research is more on the theoretical side of trying to understand what it is that we are seeing, or what observational astronomers see. So specifically, my research is in trying to understand these two very enigmatic entities in our cosmos, what we call dark matter and dark energy, and how they essentially interact to create the universe as we see it today. And understanding really what it is that they are. And so the term dark, I think, is an interesting one, because it, in one sense, refers to the fact that we don't visually see what it is that this dark matter could be. We think it's a kind of particle, probably. But dark, in many ways, is also just a reference to our lack of knowledge of what these concepts are. So we think dark matter is a type of species of particle that generates most of the gravity in the cosmos, and if in fact had it not been there, then the distribution of galaxies as we see it today, and subsequently the planets and the life and so on, would have looked very different, because dark matter is ultimately the kind of invisible skeleton and the scaffolding that holds up the visible cosmos. Dark energy, and I think sometimes people get a little bit confused by the distinction between dark matter and dark energy, because people possibly think of the whole E equals mc squared business, where energy and mass are the same thing. But dark energy actually plays a very opposite role to dark matter, where dark matter is what generates gravity and brings things together. Dark energy is instead some additional force in our universe, possibly, that actually causes things to go and fly further apart from everything else. So it drives what's known as the accelerated expansion of the universe, the fact that the universe itself is getting larger and larger, but at a faster rate. And that is being created by some kind of new field or some new kind of particle, maybe, who knows, a different kind of force, opposite to gravity. And dark energy is what that is. So they play two very counter roles. But of course, if we can't see and touch and taste or whatever any of this stuff, then how do we actually study it? Well, that's what my research is about, really, which is essentially making theoretical models of what we think these could be, and then essentially teaching supercomputers, as you talked about right at the beginning, the laws of physics according to what these models suggest they might be, and then essentially creating virtual replicas or virtual copies of the universe on the computer, saying that, okay, if we think this is what the universe started as soon after the Big Bang, if we think dark matter and dark energy are these most important entities that behave like this and have these physical laws associated with them, if I were to then evolve this whole system over what we think is the age of the universe, around 14 billion years or so, what would our predicted universe look like at the final day today, essentially? And then you have this virtual prediction that you can then basically take and observe exactly like one would do with a telescope, with a powerful telescope, and see what the distribution of galaxies are like, what their properties are, and so on. And then you compare with the real data and see, what it tells you, whether this looks in any way realistic, or there's certain aspects of this model that haven't quite worked out. And that's really what my research is about, really, which is making these theoretical predictions and then comparing with the data to try and figure out how we can improve our models more.
So are those simulations that you run on these computers actually quite accurate? Because my computer struggles to run Minecraft, let alone universal simulations.
Yeah.
So how do you go about simulating something as complicated as an entire universe?
Yeah, I mean, so accuracy, I think that it's unclear as to how exactly one would define what is an accurate universe. I mean, so one way we judge this is by saying, okay, we have certain data sets that we have collected and accumulated over several decades of taking telescopes and observing galaxies, such as, for example, counting the number of galaxies that we find of some given brightness or some given mass per unit volume of the universe. So we can actually make these measurements through telescope surveys and so on. And then we can run our simulations and see, do we actually predict the same distribution as a function of brightness for these galaxies? And then if it works out, then it says, okay, well, this looks reasonable because we're at least able to reproduce the abundances of galaxies as we observe them today. And if not, then maybe it says, maybe there's something missing in our model, which means that we are predicting too few galaxies or too many galaxies, and so on and so forth. So there's you have to choose certain metrics, I think, that you use to identify what is accurate and what is not so accurate. But I think what's one of the most remarkable things about this subject of computational cosmology, as it's called, and in fact the place where I work is called the Institute for Computational Cosmology in the astronomy department. And so what's one of the most amazing things about it is that as a subject, it's not all that old. It's something really that has been going on for maybe 50, 60 years, possibly. I mean, even less than that, really, if you think about sophisticated numerical calculations. And in that time, we've actually gone a very long way from having simulations that looked really nothing like what the observed universe looked like to having really sophisticated models that make very detailed predictions of not just the large-scale distribution of galaxies, but even the sort of intricate properties of what we might find inside specific galaxies. And we're now able to do calculations like creating near exact replicas of what the local group, which is essentially the collection of the Milky Way and the Andromeda galaxy, our nearest neighbor, and its sort of satellites surrounding galaxies. We've recently in Durham actually done a big calculation that is able to reproduce these properties really, really, very accurately. To answer your question about the computers, I mean, I think this is where the supercomputer aspect helps, which is that a supercomputer essentially is, having, tens or maybe in some cases hundreds of thousands of very powerful computers, maybe like the laptop you use to run Minecraft possibly, but having 10,000 of those running together to work towards one particular problem. So these are very computationally, laborious tasks. And certainly I think while you could do small simulations on a laptop, like the ones you and I might own, some of the biggest problems and most complex problems, I think you really would need a supercomputer to answer. And they tend to be pretty good for solving many of the equations that come up in physics and in astronomy and so on. And Durham is actually home to some of the most advanced supercomputers that we have, which is one of the real benefits of doing this kind of research here, which is that just two doors down from where I work, you can actually just go into the machine room and see the servers operating with thousands of disks and stuff like that. So it's really very cool, actually.
Maybe I should go play Minecraft on there. So you've got like these powerful supercomputers running these reasonably accurate simulations of a universe, but how do you know like kind of what sort of laws of dark matter and dark energy to sort of plug into them? Are you like kind of throwing darts at a dartboard, or is there more kind of theory crafting behind it?
I think it's probably, I would say that you don't just go in completely blind. I think that would be a slightly thankless, possibly fruitless task, because this whole dark sector could have so much going on in it, and there could be so much physics that extends beyond the normal physics that we are sort of used to with ordinary matter, that if we had no sort of basis to go by, then I think it could be quite an exasperating task. But I mean, I think there are certain aspects of dark matter that we know have to be the case. Otherwise, well, we would have discovered it in some other way. So, for example, we know that gravity has to be a very fundamental aspect of what dark matter is able to do. And Einstein's laws of general relativity and so on basically say that gravity is essentially sourced by, well, not even Einstein. I mean, go back to Newton, and Newton's laws said basically the same thing, that the laws of gravity, or gravity, is basically generated by something that has mass to it, and so it weighs something. And so we know that it can't be a completely weightless, massless particle, because we need to source the gravity appropriately. And then we said, okay, fair. Well, we can then see, how low this mass could be, or how high this mass could be. Well, we start with, say, low mass particles first, and it turns out that if you have really, really low mass particles, such as, things like neutrinos, which people back in, the 70s and 80s thought could potentially be the dark matter, because neutrinos also don't interact with light, so they're dark in that sense. Well, if the dark matter is that light, then it turns out that it's actually very difficult to form galaxies, because galaxies form in regions where there's lots of gravity, so that all the sort of gas can sink in and cool and form stars and so on. And fast-moving particles like neutrinos, these really light ones, actually end up counteracting the effect of gravity, because these particles always kind of want to buzz around and zip around the universe. And so when people did calculations of the first neutrino-based cosmologies, we actually found that the distribution of galaxies looked nothing like what was observed in the real universe. So that basically told us that, okay, maybe dark matter needs to have mass, but it can't be something that is too light. And so you can basically use these kinds of rungs to help build up your knowledge base, and sort of, improve the models further. Then, for example, we know that dark matter can't be something that interacts with ordinary particles, like electrons and protons and photons and stuff in any very significant way, because had that been the case, then, we might not have called it dark matter. We would have just called it something else, because it would have been quite easy to detect it. And so this is kind of how we say that, okay, it can't have these properties, so let's then try what else could be the case, and we put those into our model, and then we basically test how different features of dark matter could actually manifest in the galaxy distribution that we are predicting at the final day. And then we actually take our telescopes and do targeted measurements and see, do we actually find these signatures of these new dark matter properties? And if not, then that actually tells us then maybe dark matter doesn't have this property, or it has it in a very, very tiny level. So you can kind of constrain things this way. So it's constantly sort of going back and forth between theory and data.
Okay. So what are like the prospects for your current research then? Do you find that like no matter what you throw at it, nothing seems to stick, or are there sort of promising sort of possibilities for dark matter?
Yeah, I mean, so I think, there's, I think it would be unfair to say that nothing seems to stick, in the sense that, as I was saying before, the models of dark matter that we are kind of testing these days, and the kinds of simulations we're producing, end up producing virtual universes and making predictions that seem to be holding out against the data pretty well. So clearly we can't be going completely wrong, because otherwise, our simulations would not look anything like the real universe or the real data. So I think, but that's what makes it kind of a little bit challenging at the same time, because we know that we can't change the properties of dark matter so significantly that the predictions that we've made so far that seem to work out well with the cosmos suddenly then break. Okay, because if we do that, then we've kind of like undone the work. Right. It's like, so why are we coming up with this new theory where we know that it doesn't work out in the first place? And so what that ends up doing is it sort of constrains and narrows down the sort of parameter space of what other features the dark matter could have beyond the standard theory of dark matter, which is what we call cold dark matter, which is where the dark matter particle is mostly just, creating the effect of gravity, and the particles seem to be, pretty devoid of any kinds of, motions and velocities in the early universe. And this cold dark matter model is extremely powerful and very predictive in nature, in that we can make very definitive predictions, and many of these tests seem to have worked out over the last couple of decades or so. So now people are trying variations of it, but in a way that doesn't actually break the successes of the cold dark matter model. And so that then pushes us to trying to identify features in the data that we have not yet been able to constrain very accurately in observations. So, for example, by looking at the properties of the really faintest, tiniest galaxies, what are known as dwarf galaxies, or looking at properties of galaxies in the very, very early universe, so just a few 100 million years after the Big Bang, for example. These two regimes seem to be the places where different models of dark matter make the most different types of predictions in a way that hasn't been fully constrained away just yet. And so that's why things like the James Webb Space Telescope is really very exciting, because James Webb is taking lots of amazing data off the early universe, basically this epoch that up until now has been studied only kind of, with some relatively good data, but not with maybe the fidelity that is needed to be able to definitively prove apart one model of dark matter from the other. But that is actually something we expect to be able to do, hopefully in the next 5 to 10 years or so. So I think that makes it very exciting, that many of the things that people have essentially been saying that, we will be able to pin this down and really say that this is what it is, when James Webb or new telescopes, other kinds of telescopes based on Earth and in space come online, we can actually finally be able to test those theories, I think.
I guess that anticipation's been building up for some time. Huh?
Yeah, absolutely. And I mean, especially for JWST, I have colleagues and friends who have been kind of involved in the project for many years, and some of them actually started their PhDs maybe like 10 years ago, thinking that next year I will be able to start working on the data from this telescope. And obviously it is only last year that the telescope has gone up into space. But I think with all the amazing data that's coming from it, I think it's really been worth the wait. And already I think there's lots of interesting stuff coming out from it that is, some people think might be potentially breaking our understanding of cosmology and galaxy formation. Others, including myself, are probably a little less convinced by it. But I think that's the exciting thing about these new projects, that you never quite know what you're going to find.
I think kind of going back to what you said at the beginning about the whole qualitative and quantitative stuff, like I don't really, I guess, appreciate fully the maybe more quantitative side of the JWST data, but even like the images that it's taken, like of the pillars of creation, you can see sort of so much more detail than in the old Hubble images, and it's really breathtaking to look at.
Exactly. And I think there's I think James Webb sometimes gets painted as this like telescope that is predominantly looking at the very early universe and will therefore tell us about how the first galaxies formed and what dark matter is and so on. But it's really taking so much amazing data at more recent epochs and things that are closer to us. And what that does is, as you were saying with the pillars of creation, for example, by revealing so much more detailed information about things that maybe we'd already seen with Hubble or other telescopes, what it does is that it can now enable us to find out even more detailed aspects of the physical processes that are going on in these entities, and how stars are being created in these kinds of nebulae, and what dust does to sort of change our perspective on what things look like. And that's where JWST is really powerful, because it has this sort of infrared capability that is able to peer through dust, which with Hubble we couldn't, for example. So there's lots to learn even about just galaxy formation as a concept beyond just the cosmological implications of things.
I find it quite exciting to think about like what sort of knowledge could be, I guess, taken for granted in the future, like we do now, with what we know. I guess it's easy to get carried away, like, oh yeah, we're gonna learn so much crazy
Yeah.
stuff from this, and
Yeah.
maybe that's a bit optimistic, but I think it's very exciting to speculate
Yeah,
about.
you never know, like the stuff that we are kind of talking about as, real big unknowns in our understanding of the cosmos and what it's made of and so on. Maybe 100 years down the line will just be standard parts of
Yeah.
high school science textbooks, right? And that's kind of the way it is sometimes.
Yeah, if you could take like the quantum mechanics part of my A-level textbook back a couple hundred years, I think
Right.
that'd blow some minds. It's quite funny, I guess.
Yeah, no, exactly. And I mean, quantum mechanics, I think, is a good example of that, in that, again, if you go back to the earlier 20th century, there was so much debate and controversy over the kind of predictions of quantum theory and its implications. And some of those philosophical aspects are still debated now, but, at least quantum theory generally is such an everyday part of our lives through all the technology that we're using now to talk to one another, for example, or to record things and use on our computers and so on. It's sort of everywhere, really. But it's, a subject that's just about more than 100 years old.
So going back to what we were talking about a bit earlier, with the you were talking about how the cold dark matter sort of model. It seems that people are quite, I guess, attached to this model from what you were saying. Do you think that's like a sensible approach, or do you think that maybe by, I guess, wanting to stick to this model that kind of fits a lot of the data, do you think that maybe we're missing out on other potentially correct, well, air quotes, correct models for dark matter?
That's a very good question, actually. And I think, there's, as with everything, I think there's a yes and a no to that response. So I think there's a very good reason why people are attached to the cold dark matter model, which is that, people have proposed various alternatives to it and various ways to try and disprove maybe the predictions of the cold dark matter model, but in general, it seems to have held up pretty well. And when a theory is able to do that consistently, but at the same time is also able to make certain predictions, which can then, 5-10 years down the line, be found, which we have done in one or two cases of the cold dark matter model's predictions, then I think that speaks well to the testament of a theory. But I think you're also right in the sense that fixation upon something can give you a little bit of tunnel vision, of course. And I would say that, there is one big issue that I personally see so far with cold dark matter theory, which is not to do necessarily with the astrophysical side of what its predictions are or how well it compares with the observed universe, but rather just the fact that we haven't yet detected a cold dark matter particle. And this is despite quite a lot of effort on the part of the astronomy community and the particle physics community to try and detect something like this. So when cold dark matter was sort of first being studied and proposed in the 1970s and 80s and so on, there was a very specific type of cold dark matter particle that was hypothesized as being the right thing to do, a right thing to look for, rather, which is a class of particles called WIMPs, or weakly interacting massive particles. And the reason why they became popular is because not only did you manage to get a sort of prediction from an astrophysics perspective of reasonably accurate representation of galaxies in the cosmos, but from the particle physics side of things, you could actually say that these particles have a specific property about them, something called the cross-section, which can be predicted directly from particle physics. And if these particles have that cross-section, you actually predict an abundance of cold dark matter particles that is exactly equal to what we think is the abundance of dark matter in the universe. Okay, so the particle physics motivation translates to the cosmological inference of dark matter, and how much dark matter we think there is in the cosmos. And so that's why this became a very popular model and candidate to look for. And so if we think that this particle has this particular cross-section, which basically just means, how easily or how much of this dark matter there is, then we should be able to test this by actually building detectors that are somewhere underground, so that we are devoid of interference from other particles streaming through the atmosphere. And then the idea is that when these particles of cold dark matter then stream in through the atmosphere and penetrate through the ground, which we think should be happening all the time. So there's particles of dark matter we think that is flying through our bodies right now as we speak, obviously without any noticeable interaction. But these tanks are basically there to have been built to try and detect these dark matter particles as they stream in through, and then knock basically the atoms inside the fluids contained within these tanks, which are basically inert fluids like xenon and argon and so on. And they create these like jets and trajectories in this fluid, which we can then try and map to some kind of dark matter particle or particle interaction that has happened. So people have been building these really expensive experiments, really high precision, high quality experiments for a couple of decades now. And, there have been tentative claims of, we've seen something that we, don't recognize as being a particle from the standard model of particle physics, basically the typical particles that we know of that we can see. But many of these claims have then kind of disappeared as saying that, okay, well, actually, it doesn't really turn out like that really happened. And, there are other predictions that the cold dark matter model makes of how the particle might be observed in space, for example, through the production of what's known as gamma rays, because these particles tend to sort of annihilate as they meet one another. When two dark matter particles hit one another, they basically annihilate into photons, and the energy of these photons are basically in the energy range of gamma rays. And people have said that, we've actually detected with a telescope called the Fermi Space Telescope, actually, a gamma ray emission across the Milky Way that looks very much like the signal expected from cold dark matter particles when they annihilate. But then people obviously got very excited by this, and then it turns out that there could be other entities in the Milky Way, such as these types of stars called pulsars that generate very similar types of energy signals. And so that's kind of like poured a bit of cold water on that particular thing. But so this kind of thing has happened quite a lot. There have been these tentative claims of potential dark matter detection, which have then kind of gone away. So I would say that fixating just on cold dark matter might result in the danger that we keep proceeding down the line to try and narrow down exactly what cross-section cold dark matter could have and what annihilation signal it could have. And maybe the dark matter is something completely different, which behaves like cold dark matter for all intents and purposes, but it might not be a WIMP-like particle. It might be a different type of cold dark matter, in which case we might not actually ever expect to see it in underground detectors or as gamma ray annihilation. And so that's where I think doing these theoretical calculations and stuff are really helpful to see what else the dark matter could be. And therefore, when we have a reasonable alternative, then to say, okay, let's try and see if we can find any signatures of this model in observational data, and then think about what might be the prospects for detecting the actual particle itself.
So kind of covering all our bases and...
Yeah, I think so. I think you have to be, because, it is such a... I mean, it's called dark for a reason, right? I mean, we just have very little idea of what it could be. And, there's a whole community that is actually invested in this idea that dark matter isn't a particle at all, but rather that the reason why dark matter was the dark matter idea came about in the first place is to try and explain anomalies in the motions of stars around galaxies, where people found that stars in the very exteriors of galaxies moved at roughly the same speed as stars in the very centers of galaxies, whereas standard gravitational theory would say that you should slow down as you go further out from the center of the galaxy because there are fewer stars on the outskirts, and so the gravity should weaken. And so dark matter was introduced as this idea as the sort of external gravitational source that surrounds galaxies rather, that allows stars at all distances to move at roughly the same pace. So there's a whole community that actually says that, well, who says that it has to be another particle that is creating gravity? Maybe it's just that our laws of gravity are incorrect. And so there are some people who are invested in this idea that maybe the stuff that we are observing with these anomalous motions of stars and so on is nothing to do with a different or a new particle. It's just that Newton's laws of gravity or Einstein's laws of gravity are incomplete, and that they need to be modified such that they kind of behave on different scales in different ways. And, it is argued sometimes so I don't personally subscribe to this idea because I think there's quite a lot of evidence, I think, pointing to the contrary in terms of how the particle dark matter idea seems to be a much more solid. It seems to be on a much more solid footing. But I think it's sometimes argued that maybe this modified gravity version of things is a more elegant solution. But personally, to me, I don't see that as being any less radical than, say, just hypothesizing that there could be another particle in the cosmos. So yeah, it's a very wide open field. So there's lots to do, and that's kind of nice because it means that there's so much research still ahead of us and so many avenues to explore.
Particles or better gravity. I wonder which one will be in the high school textbooks.
We'll see. Yeah, I mean, I think maybe it's worth putting some wagers down with people to see 30 years from now what becomes the basis for what we find in our textbooks.
I place a bet on every dark matter theory, then I can't lose.
No, exactly. But knowing the cruel nature of nature, I guess it'll probably turn out to be none of the theories of dark matter and something probably completely different.
I'm sure it'll be quite elegant in either way.
Mm-hmm. Yeah, exactly.
Okay, maybe we should start to wrap up then. I guess, Sownak, do you have any kind of hopes for your research in the near future?
I do, of course. Yeah, I mean, I think you are always kind of hopeful that something really paradigm shifting will happen in the next few years or so. And I think probably every generation of astronomer or cosmologist has said this, but I really think that now, more so than ever before, we're really moving into a really unprecedented epoch of discovery when it comes to astronomy and cosmology and learning about the fundamentals of our existence. And that is due to two things, I think. One being just the improvement of the sophistication of the technology that we're using to study these from a numerical perspective and do these very, very complex, large calculations. But also, I think it's been simultaneously been met by an incredible increase in the technology that goes into building the telescopes that we're using to make observations. So we spoke about JWST, obviously, but there's several projects coming online in the next 10, 15 years that will be both ground-based and space-based that will enable us to sort of peer into, regimes of our universe that have been, thus far been completely inaccessible to us. And I think that will really provide us with an opportunity to study the cosmos at a level of detail that's been really unprecedented and will really be incredible for being able to understand this idea of dark matter and dark energy quite a lot better. I think that is a good enough reason to be very optimistic, I think. I'm really kind of trying to think about what are new ways to test our theory. And as we've seen from things like LIGO and gravitational waves and so on, it's just a different way of looking at the universe can reveal so much more information than we had previously and really unlock a completely new branch of study in some cases.
Yeah, it's never any better time in the present, right?
Yeah, exactly, yeah.
So, why would you say why would you say your research is like important to like in a maybe a more sort of practical sense. Obviously, there's the kind of theoretical side, like furthering our understanding of the universe and all that. But if like Owl, do you think there's any more sort of practical reasons for research?
Practical reasons for research, generally, yes. I mean, so maybe specifically dark matter research. I mean, I don't know if there's any practical applications you could ever use dark matter for in that sense. Besides, I think just furthering, human curiosity and understanding where we come from, which I think are as important questions as anything. There's a few other things. I mean, of course, when you do the kind of work that I do, for example, which is very computationally oriented. There's a lot of data science and statistics and stuff involved in it. So, there's a lot of transferable skills, really, that one picks up over the course of doing this kind of research in a PhD or in a graduate degree of some kind. And so quite a lot of people, of the students that we have trained in Durham, for example, have then gone on to work in data science, for example, because the same kinds of skills can be applied there. So you're training the next generation of, students to a very broad range of careers. The fact that we do, heavy computational work is important because these supercomputers can be used for not just astronomy, but I mean, actually over the course of the pandemic, there was a subset of students here who were doing work with COVID researchers to like model COVID viral transmission and so on and so forth, using the Cosmos supercomputer that we have in Durham. And, the same supercomputers and same kinds of algorithms in some cases are used in things like climate modeling and in things like, understanding the hydrodynamics of Formula One cars and things like that. So I think there's lots of different aspects that surround why this kind of work is practical and useful. But specifically dark matter and galaxy formation and stuff like that, I would say it's mostly the intellectual curiosity and the pursuit that I think is the greatest achievement that we can think of as for society.
I think it's always interesting when things end up having like uses that maybe they weren't initially thought to have, and then later on, you find out actually this is useful because of XYZ. So it's like in many ways, I guess we can't really know how it is useful until we sort of investigate it.
Exactly. Yeah. I mean, and there's no better examples of this than say like how Maxwell's laws of electromagnetism have helped eventually develop the electronics that we have today. How Einstein's theory of general relativity has been used to make GPS navigation much more accurate in Google Maps and so on. How the development of finding a convenient way to share data at CERN, the particle physics laboratory, led to the eventual development of the World Wide Web, for instance. So you never quite see, maybe at the time, what the immediate benefit to society will be, but further down the line, I think things become a lot more apparent. So never say never. Maybe there will be some useful dark matter at some point in the future.
Yeah, we'll see, I guess.
Mm-hmm.
So do you have any sort of closing remarks, any like websites you want to plug, anything like that?
Closing remarks. Well, so so one of the things I would definitely say is that hearing about all of these things of equations and computing and stuff like that can seem like a very daunting, slightly overwhelming thing, perhaps, which might make you think that, oh, this is maybe quite a hard subject to get into. And, it's not to say that it's easy necessarily, but I think astronomy is really a great subject because I really think it's a subject that is open to everyone. So when I was growing up, for example, I never really wanted to be a physicist or an astronomer or anything like that. My dream was always to be the manager of Manchester United. That didn't quite work out, and I then wanted to study economics and so on. So, like, going into physics and astronomy was very much a sort of last minute thing for me. So I was really never one of those people who was academically super brilliant or something like that. It's just kind of like I eventually got interested in physics, and that kind of drove everything afterwards. So, I think pursuing your passion is probably the most important aspect to all of this. And I think even if you feel like you might not be ready for the mathematical burden of it all, I think just one's excitement for these things can help you get past a lot of these kind of stumbling blocks in life generally. In order to maybe plug something, maybe one thing I can point your listeners to is a website that several of us in Durham constructed a while ago. Actually, so when I was a PhD student here back in the day, so in 2016, Durham's astronomy group was invited to present an exhibition at the Royal Society Summer Science Festival in London. And we built a number of outreach tools and stuff like that, which is really one of the best parts of doing astronomy research, really, is being able to kind of showcase this stuff to the public. But we built a website for this, which is called galaxymakers.org, where you can go on and essentially do things like simulate and create your own universe using online web apps, and you can change around things like dark matter and black holes and stars and what they look like and how much there are of these things, and basically create virtual copies of universes on your browser, and then the app kind of then tells you how good your personal universe has been compared to the real data and stuff like that. So it's a cool application to try out. So if people are interested in learning more about this kind of thing, then I think that's a nice place to check it out. So www.galaxymakers.org.
Excellent. Wow. I'll be having my fingers crossed for your dark matter research, Sownak. Hopefully it's all over the papers soon.
Yeah. Yeah, absolutely.
Thank you so much for coming on.
It's been my pleasure. Thanks for having me.
I'll see everyone listening next week. Thank you for listening. Bye.